So in this video, we'll talk about the seminorms and the local convexity. So let's start with some terminologies. So we say a function p from a vector space to real number is a seminorm if it satisfies the following two conditions. So first, we have the triangle inequality, or the subadditivity, Py. So subadditivity. And second, it preserves the scalar product. Is equal to Px for every scalar in the scalar field, and of course for any two vectors in the space. And as we'll prove shortly, these two conditions will imply that it is non-negative for every x in a space. So combining that it is non-negative if a seminorm is 0 implies that x is 0, then P is actually the norm. And we'll prove the final main result of this chapter at the very end of next video. So other way of saying that is that the null space of P is the trivial vector space. Next, we have separability, or separating, of a family. So P is a family of seminorm, say P alpha, for alpha in a index set. We say that it is separating on X, if for every x in the space that is non-zero, we can find a seminorm such that P alpha for x is non-zero. Then we say it is separated. And as we'll see, this is actually the same as P of 0. So this is same as saying for every x not equal to y in a space, there exists a seminorm that P alpha of x is not equal to P alpha of y. These are equivalent. Next, we have the concept of absorbing. So a subset A is absorbing if for every vector in the space we can find a positive number such that x is inside TA, we'll say that it is absorbing. So one important example of absorbing set is in the theorem 1.15, we prove that if V is a neighborhood of 0 in topological vector space, then MV, union of MV, will eventually cover the whole space. This actually implies that V, or every neighborhood of 0, is absorbing. This is a very example of an absorbing set. So now we can define the Minkowski functional, which goes as follows. So given a set A that is absorbing, do we require to be convex here? I don't think so. Oh, yes, we do. Okay. So we also require to be convex. So if a subset is absorbing and convex, we can define a functional mu A from the vector space to the real numbers in the following way. So we send X to the infimum of positive numbers such that X over R is inside A. Or equivalently, we can put the R to the other side. So the main objective of this video is that we want to prove we have a one-to-one correspondence between seminorms. That's right. One-to-one correspondence between seminorms and the Minkowski functional, where this subset A is convex, absorbing, and balanced. This is the main objective of this chapter, and we will prove this in the next 3 theorems. And in next video, we will also prove that if we have a family of, so we have family of separating convex, we don't need a convexity here, separating seminorms, we can define a topology that is locally convex. So we'll prove this in next video. So locally convex. So okay, let's start with the basic properties of a seminorms. So theorem 1.34. So let P be a seminorm as above on X. So first, P0 is 0. Second, you have P of X, P of Y is smaller than P of X minus Y. C is non-negative. D, the null space of a seminorm is a subspace. E, the set B defined to be the points such that seminorms are smaller than 1 is convex, balanced, and absorbing. And we will prove a converse later. And P, the seminorm P is equal to the Minkowski functional given by the set B. So the proofs are simply follow from the property we have. So A, in the second property, the scalar rule of a seminorm, we have alpha x. Then we can take the alpha outside. Then we just put alpha equals 0. Then we got A. Second one, what we do is we look at P of X and we apply the subadditivity to it. We have P of X plus P of X minus Y. So just move P of Y to the left hand side. We have P of X minus P of Y is smaller than or equal to P of X minus Y. Then exchanging X and Y, we have that P of Y minus P of X is more than or equal to P of Y minus X. Then by the scalar rule, we can move a minus 1 outside, which is just 1. So the right hand side is the same. So we can combine these together and get a result of B. So next, to prove C, you can put y equals 0 in B, or you can just calculate it directly. So 0 is P of 0, and again, we just write 0 as x minus x, and use the sub-additivity. And the scalar rule, we got that, is non-negative. So these are very easy. Next, we have the null space of the seminorm is a subspace. So obviously, 0 is in this space. Let's call it N. As P of 0 is 0. And next, we want to show that it's closed on the addition and scalar multiplication. So what we do is we choose 2 points in the space. So we have P of x equal to P of y equal to 0. And for any 2 scalars in the scalar field, we calculate the seminorm of alpha x plus beta y. And by the both rules of the seminorms, we have which are both 0. So ax plus beta y is in a null space. So and it's a subspace. Finally, we have we define the new set called B, which is vectors such as the seminorms is smaller than 1. Then we want to prove first convex. So that x and y be inside B. So we have P of x and P of y is smaller than 1. And when we consider the convex combination of these 2 points, we calculate its seminorm. And again, by the 2 rules of the seminorms, it is again t times P of x plus 1 minus t times P of y. And this is obviously smaller than 1. So this proves that B is convex. Next, we want to prove that it is balanced. And this is also obvious by the scalar rule. So x in B and a scalar. And we just calculate the seminorm alpha x. And because it is positive, this is non-negative. So this is smaller or equal to P of x, which is smaller than 1. So ax is inside B. So balanced. Finally, it is absorbing. So for the absorbing part, let's prove this together with the equality P equals mu B. So what we do is we fix an vector and we choose a positive number such as larger than P of x. Then we just move s to the other side. We have s over s is smaller than 1. This implies that x over s is inside B. Then by the definition of a Minkowski functional, mu b of x is smaller than S. And by the way, this part here proves that it is absorbing. So we prove a third property of a set B. And this proves that mu B is smaller or equal to P. So for the other part, we just consider the scalar that is smaller or equal to the seminorm. And again, we put T to the other side. P of T over X over T is larger or equal to 1, which means that X over T is not inside B. So mu B of X is larger than T. So this proves that mu B is larger or equal to P. So this finishes the proof that mu B is equal to P. And next theorem, we want to prove that the Minkowski functional can become a seminorm if the set satisfies some necessary conditions. So theorem 1.35, given the set that is convex and absorbing, then by definition of the Minkowski functional, we can define it. Then it will have the properties, the subadditivity, and it will preserve positive scalar products. So Tx will be T times mu of X for T positive or non-negative. Then from these two properties, these is almost a seminorm, except that we want T to be any real numbers. So to do that, we need the set A to be balanced. So if it is balanced, it implies that this is a seminorm. And finally, we define two extra sets. One, as before, B is a set that mu A of X is smaller than 1, and C is smaller or equal to 1. Then we will have a inclusion that B is in A is in C, and the Minkowski functionals are the same. So to prove A, we choose T and S in the following way. So T chosen to be mu A of X plus epsilon, and S chosen to be mu A of Y plus epsilon, goes on epsilon positive. Then by definition of a Minkowski functional, these 2 points X over T and Y over S are both in a set A. Then we look at the point X plus Y over T plus S. And actually, this is just the convex combination of the previous 2 points. So we can decompose the sum into a convex combination of X over T and Y over S. This implies that by the convexity of the set A, so by convexity of A, X plus Y over T plus S is also in A. And this implies that the Minkowski functional acting on x plus y is smaller or equal to t plus s, then by the definition of t and s, we have that is equal to mu x plus mu y plus 2 epsilon. And this proves the part A of the theorem. Next, we want to prove it preserves the positive scalar multiplication. And it's trivial. We just write down the definition and it follows. So mu a of tx is by definition the increment of r positive and tx over r that is in A. And we can just take the t outside, right? So take a t outside. Then the rest of this is just a definition of mu a of x. So we're done. Mu a of x. Of course, this is only true for t positive, and for t0 is trivial. And in part C, if further A is balanced, then mu a of x will be the same as mu a of minus x. And this combining with B and by B, we have mu a of t, that's right, alpha x is the absolute value of alpha times mu a of x. So this gives the seminorm. It's a seminorm. And finally, we have two sets. B equals mu a of x smaller than 1, and C equals mu a of x smaller or equal to 1. Then by definition, we immediately have that B is inside A is inside C. This is by definition. Then from this inclusion, because larger set needs smaller number to include a point, so actually the functional of C is the smallest, smaller equal to mu A, smaller equal to mu B. So what we need to do to finish the proof is mu B is smaller than mu C. So what we do is we fix a point in a space and we choose T and S and T such that Px is smaller than let's say mu C of x is smaller than S smaller than T. Then we first move S to the left hand side. We have this is mu. So this is also mu. Mu C of x over S is smaller than 1. Then by definition, this implies that x over S is inside the set C. Then by the definition of the set C, this implies that mu A of x over S is smaller than or equal to 1. Then now what we do is we multiply it by S over T. We got mu A of x over T is smaller than or equal to S over T, which by the choice we made, this is smaller than 1. So this proves that x over T is inside B. Hence, mu b of x is smaller than t. And because this is true for every t, such that t is larger than mu c of x, this implies that mu b is smaller or equal to mu c. So this finishes the proof. So finally, we want to prove that the converse is true. So namely, if we have a convex, balanced, absorbing neighborhood, then it can become a separating family of seminorms. And this will finish this video. So theorem 1.36. We have a local base that is convex and balanced. And because it is a local base, every set is absorbing. So this is a trivial absorbing. We don't need this condition because it holds automatically. Local base. And as before, we just write the Minkowski functional as mu v. Then we have the following properties. So v is just the set we defined before, the Minkowski functional with values smaller than 1 for every neighborhood in the local base. And second, this family of Minkowski functional, where v is in a local base, is a separating continuous seminorm on X. So the fact that it is a seminorm, we already proven in the previous theorem. So we will prove the other two properties. So starting from A, we look at a point that's inside V. Then by openness of V, there exists a t that's smaller than 1, such that x over t is still inside V. And this implies that mu v of x is smaller than 1. Next, on the other hand, if x is not inside V, when x over t is inside V, x is not in V. So when x over t is inside V, this can only be possible for t larger or equal to 1. So this also implies that mu v of x is larger or equal to 1. So this finishes the first part. So v is equal to mu v of x smaller than 1. And essentially, this is true for any convex, balanced, absorbing open set. So yeah, it need not be a neighborhood. So next one, we want to prove the other two properties. So seminorm is proven. So proven in previous theorem. Oh, which one's that? I think it's C. So next, let's prove continuity. which is really easy. So remember that this functional is from the vector space to the real number. So we just choose a real number, then we find a neighborhood such that we can control the points, such as Seminorm is inside R, then we're done. Now, by the property we had before, P of x minus P of y, taking absolute value is smaller than or equal to P of x minus y, and we want this to be smaller than R, right? Then, by the definition of the Minkowski functional, oh, this should not be the Seminorm. This should be the Minkowski functionals. Well, they have the same property, so that doesn't matter, as it is a Seminorm now. So we just choose x minus y inside R times the neighborhood of V, then we're done. So the continuity is trivial. Finally, we need to prove that it's separating. So we need to prove that for any point that is non-zero in the vector space, we can find a norm such that mu v of x is non-zero. So this is also trivial because there exists v such that x is not in V, and V is inside the local base. So mu V of x is larger than or equal to 1, which is clearly not zero. So we're done. So what we've done so far is that the Seminorm and the Minkowski functionals are actually equivalent, as long as we choose the neighborhoods or the set correspond to the functional to be convex, balanced open sets. And in next video, we'll prove that these family, so the separating family of the Seminorms and we will denote it by a curly P, will induce a topology. On the topological vector space. And as we see before, if we already have a topology with a local base B, we can construct this separating family of Seminorms, and this will again give you a topology, right? And we will prove in next one that these are actually equivalent, so nothing is going wrong here. So this we'll do in next video. And after that, we'll prove the last main result of this chapter, the normable, if and only if it is bounded, there is a bounded convex neighborhood. Exists convex bounded neighborhood. And using the theory of Seminorms, it will be very easy. And of course, it's of zero. And we'll stop here.